Okay, hello everybody. We're just going to wait a few minutes, maybe three minutes just for everyone to join. As I said before, we're just waiting a few minutes for everybody to join. Okay, cool. I think that's enough time, so we can get started now. So, just a brief introduction on myself. So, my name is Nur'ain Areff. I am a consultant at Optimum Solutions. I studied electrical engineering at FITS. And at Optimum, I work mainly in the simulation engineering space. So over there, I create some digital twins. I also work with a lot with model-based design. Besides for that, I also work with computer vision and I do a bit of data analysis. So today, in this webinar, we are going to be talking about how we going to design our microgrids with using simulation as well as AI. So first, we are going to go through the agenda. So we will do a brief introduction on Optimum Solutions, who we are and what we do. After this, we will go through why we need to use or why it is useful to use simulation tools in the design process. And our main focus is going to be on our example, which is with super solar. So what we are going to do in this example is we are going to first have an optimization. So we are going to ensure that we size the components correctly of the microgrid. So this will ensure maximum cost savings. And then after we size our components of the microgrid correctly, we are going to use a simulation to then test the parameters of the solar as well as the battery. And the first two, the optimization and the optimization and simulation is part of first principle modeling. So this is where we use our physics laws to model. After this, we will then go to artificial intelligence and machine learning, and then we will show how we can use predictive maintenance to predict the remaining useful life of the battery systems, and this also helps with our maximizing our cost savings. And then just to mention, as I said before, the optimization and simulation is the first principle modeling, which uses physics laws mainly, and then the artificial intelligence and machine learning is using the data-driven modeling, which has the input and output simulations. Also, just to mention for this webinar, we will send a recording of the webinar with the slides as well as the scripts that will be shown later on. Okay, so as I said before, we are just going to go through a brief introduction of Optimum Solutions and who we are. So first and foremost, we are a high-tech consulting and engineering firm, and we specialize in creating technical business and engineering solutions. And this is because we like to make a real-world difference to our clients. So our three main areas which we specialize in is artificial intelligence, model operations, as well as simulation engineering. And then some highlights about us is that we've been a trusted partner to MathWorks since 1992. We also have been involved with the development of some of MathWorks products. We have delivered more than 250 projects locally as well as internationally, and we have a skilled consulting team that consists of more than 30 engineers as well as developers. Just to have a bigger overview of our competencies, like I said before, it includes artificial intelligence, model operations, as well as simulation engineering. And this slide is just more for you to look at for some of the projects that we have done. One to mention within the simulation engineering space is that we have performed a power quality analysis, and what we did was we had data from a logger which we analyzed, and then we did a power quality analysis, and then we had optimizations in this such as power factor correction. And this was one of the projects that I found very interesting. And also there is a case study later on for this project, so if anybody wants to find out more, I left it in the slides, and if you want to talk more about it, you can message me and we can talk a bit more about it. Okay, so that was just a brief introduction into Optimum and who we are and what we do. So now we will get into the more technical aspects of the webinar. So first, I would actually like to talk about why simulations are useful. So the first thing that comes to mind is that it is very cost effective. So what we can do is we can optimize systems before deploying it into the real world. So this ensures that we produce it at minimum cost. What we can also do is we can integrate different renewable systems within, say, if we have a simulation of a grid and then we want to integrate renewable systems, it's very easy to first do this within simulation before we spend money on buying actual components, and then we can test it and verify that it works under different conditions. And then the next step would be that we can run all different types of studies. So we can run fault studies, harmonics, as well as load studies. And then this can give you insights into variables that you might not be able to measure. And it can also predict faults that haven't occurred yet. And then the last thing which I touched on with the integrating renewables and running fault and harmonic studies is the testing and validation. So just to reiterate myself, within the simulation, you can safely test all possible scenarios as well as conditions. Okay, so now for the use case that we are using. So this is what we are going to use for the remainder of the webinar. So our customer is Super Solar, and their challenge is that their energy costs are too high, and this is due to Eskom as well as their reliance on diesel-powered generators. So what they want to do is they want to reduce their dependencies on Eskom as well as diesel power generators in hopes that they maximize cost savings. And what they would like to do is introduce renewable sources because they have the available space necessary. They will also like to invest in assets such as solar as well as batteries, and they also want to have a greener company. So the workflow that we are going to use today consists of the following. So first, we are going to start with our optimization. So for an optimization, we are going to we're going to have power data from our super solar company, which contains the load data that they use yearly. After this, we are going to use this data within a techno-economic optimization, and then we are going to size our PV as well as our battery components. And to do this, we use the MATLAB-based environment and the optimization toolbox. So all of this is MathWorks toolboxes. Then after we get the sizing of our PV and our battery components, the next step would be our simulation. So this is where we're going to incorporate our PV and battery system with the grid as well as the load. And the toolboxes that are used for this include Simulink as well as Simscape. And then with Simscape, you have additional features and domains such as Simscape Electrical and Simscape Battery. Then in certain cases, say we run our simulation and we see that, okay, we can improve the sizing of our PV as well as our battery, then we would go back to our optimization, re-optimize our system with our new data, and then simulate it again. And then this can be an iterative process until we are happy with our simulation and we are happy with our sizing of our battery, of our solar, and how it works with our grid. And all of this, remember, is to show that we are maximizing our cost saving. So after we are happy with this, we can take an additional step, which would include machine learning. So in our case, what we are going to do is we are going to use predictive maintenance for batteries. And later on, I will get into why this helps with cost savings and why it will help overall. And the toolboxes that we use for our predictive maintenance is the statistics and machine learning toolbox as well as the deep learning. So just to mention, these examples that I'm going to show, it's straight from MathWorks, so they are not very intense examples, but they are very nice and I modified them slightly, so you can go take a look at them and I will also send you the examples as well as the scripts. Okay, so now we are going to jump into the demo. Okay, so for anybody who hasn't seen the MATLAB environment before, this is the environment. So as you can see over here, we have our, on the left-hand side, we have our folders, and this is where all our scripts as well as models are contained. Then on the far right-hand side, we have our workspace. This is where all our variables are. And then up on top, you can see there is a new button over here. And if we click this, we can see there's different types of scripts we can have. So we can have a normal script, a live script, a function. So what I am currently going to use is a live script. So in the live script, it's nice because you see that you can either show your code or you can hide your code and you can add text as well as pictures. So this is our live script. Just going to make it a bit bigger. So in our live script, so as I said before in the workflow, we are going to do our optimization first. So this, so what we are going to do in the optimization is we are going to optimize an energy mix which of a microgrid which contains a utility grid, a PV array, as well as energy storage. And the point of this is to optimally size the components so that it ensures that there is maximum cost savings as well as linear and we also consider linear degradation of the storage unit within this optimization. So there's a few steps that you have to take within any techno-economic optimization, and step one would be we have to define the correct variables. Then step two would be we define the constraints. Step three is we define the objective, and step four would be we solve the optimization problem. So starting from step one, we first define our variables. So we assume that Super Solar has provided us with the following data. So this includes the load power, the grid electricity price. So for the grid electricity price, over here it is not just static data. There is a model behind this. So what this model takes into account is it takes into account which days you are using your grid as well as peak hour prices. And then our last variable we have is our solar profile, which is our irradiance data. So this would be the irradiance data of where Super Solar wants to build their microgrid. Okay, so now that we have all our variables, now that we have all our data that we need, the first thing we do is we go to our live script. So as you can see here, it gives us nice instruction of exactly what to do. So we have to select the file which contains our power data. So we just click on this to open up the folder. As you can see, it opens up our current folder, and what I have in here is MATLAB data, which is this power one that I put over here. But you don't only have to use MATLAB data, you can use CSV files as well as Excel files. Okay, so we input our power data over here. Then the next thing we have to input is how many hours we want to analyze. So I have the data for a year, so that is 876 hours. But just for the purposes of this, I use 2,190 hours, which corresponds to 3 months, but we can use up to 8,760 hours. So, and also you can just change this as you want. Once you have the script, you can just change this to how many ever hours you want. And then it will run the optimization accordingly. And then lastly, it's the same thing as we did for selecting our power data. We select our solar profile or our irradiance data. And after we do this, we select maximum solar power as well as battery capacity. So these values can be selected according to the load data that we have. So if we have a maximum in our load data, that's how we would select our maximum solar power and battery according to that. Or it can be selected according to our price constraints. And also for these, you can change these values as you wish. Okay, so that was our step one. So now all our variables are defined. So for step two, we now define our constraints. So the first thing we do is we set up the balancing of the total system power, and then the balancing is that the storage power and the load power at all times is equal to the grid power plus the solar power. Okay, so this is our balancing of our total power. And then the next thing we need to do is we need to calculate the costs of our battery as well as for our PV. And for this over here, we don't need to calculate our grid because remember, as I said, we already have a model for the grid that we are using. So what I did was I used the following equations, which I left the link to in here, which has equations for the cost for residential battery storage as well as residential PV. And it's very easy to turn this into industrial PV or battery storage equations. We just have to get the equation and slightly modify the code. So in these equations, if you open the links, you'll see that the cost formulas give you an output of dollars per kilowatt. So what we have here is our exchange rate to convert it to rands. And also with this, you can change the exchange rate depending what it is on the current day. Okay, so those are our first two steps. So we defined our variables, then next we defined our constraints. The third step is that we have to define our objective. So remember, our objective equation is to minimize costs while maintaining enough power to support the load. So here is our equation over here where we have our total cost is equal to the individual powers multiplied by their prices, and they are all added together. So this is our objective equation for optimization. And then lastly, we solve our optimization problems. And then you can see over here the optimization problem is solved. And then I'm just going to run this to show you in real time how it works. And in the meantime, while it runs, we'll just send out a poll, because in here we don't go into detail about the cost savings, but we just like to know if that is something that anybody is interested in. So I'm just going to run it and then the poll will be sent. So it's running over here. So as you can see, it it ran 21 iterations, and it found the minimum constraint satisfied after 21 iterations. As you changed these variables over here, you'll see it will run different amounts of iterations. Cool. So now we're just going to take a detailed look at the results. Okay, I just opened it up. So for the results, I just opened it up and zoomed in to a specific day over here. So I'll zoom out and show you the whole time we have once we're done getting into the results. Okay, so as you can see, our blue over here is the PV power. So as expected, after around 12, it increases to a maximum till around 3 over here. And when the solar is high, so this means that it is giving power to the system, we can see that our grid. So once our solar is high, we can see that we no longer need our grid to produce so much output power, and then we can see that it goes lower and we actually go to negative power. So what this negative power means for the grid is that it means we are feeding back into the grid. And then so that is our grid and our solar. And as for our battery over here, we can see that we are using a little power for the battery. So this positive power is when the battery is being used. And then we can see this negative power is our battery charging. So when the battery goes negative, it's charging. And when it is positive, that means our battery is being used. And then finally, our purple line is our load power. So we basically make sure that between our solar, our grid, and our battery, that we always have enough power to maintain our load. And sometimes we have extra. So as you can see over here, the solar is above the load. So that's at those points, that's when we either charge our battery or we feed back into our grid. Okay, and just to zoom out a bit to show you, we have a lot of data um, we have here. So this is all the data that we have from our optimization. I just wanted to show you a small section just to explain our further optimization. Okay, so now we are done with our optimization. So as I said before in the workflow, we had our optimization, and after we size our components, then we go to our simulation. So this is the tool that I mentioned earlier, which is known as Simulink. So this is the Simulink environment, and the previous one I showed is the MATLAB environment. So within Simulink, we use more blocks instead of writing code. So within a Simulink, there is Simscape, which is what this model is made out from. And just to show you before we delve a bit detail into the model, just want to show you how many toolboxes there are with Simulink. So I'm just going to open this library browser. Yeah, so in the library browser, we can see that we have Simulink, we have so many different toolboxes over here. We have the, just to go down to what toolboxes we're using. So mainly using Simscape. So if we go into Simscape, we see we have Simscape battery, driveline, electrical, fluids, and multibody. And these are just all different inbuilt blocks that we can use. Just to show you a few, I'm just going to open here. So we can see that there's many things that we can use. And another way, if you are familiar with the Simulink environment, to just search for blocks, you can just double click and then search for, say you want a voltage source, and then we search for voltage. So there we have all our voltage elements over here. Okay, so now to get a bit more into the model. So over here we have our different subsystems. So here we have our grid, we have our PV or our solar, we have our battery, and we have our load over here. So this model is a low fidelity model, and we use specialized power systems within Simscape. And the reason for this is we want to simulate for long periods of times. And so the way this model is linked to our sizing is if we open this, so if you double click on a block, it just goes into the block and shows you the components within the block. And how it links is we have lookup tables. So we have lookup tables with our load data as well as our solar data. And what it does is these are all saved in variables. So here we have our load power, and over here we have our solar power. So what happens is that as it updates within MATLAB, remember I showed the workspace, so the variables will update in the workspace if we run the script with different values, and then it will update in the workspace, and then once it updates in the workspace, it will automatically update over here in our model. So that's how we test the sizing and the system sizing is correct, and if we are happy with it. And then I ran the simulation before because it does take some time to run depending on how many days you want to run it for, or within the optimization as well as within the simulation. And you can also change it over here. So right now I ran it for 5 days, and then I will just open the results again so we can go through it. So this is the results for our simulation. I again zoomed in a bit. And so as we can see, it's the same thing. So with our PV, it increases during the day and it peaks during around 12 to say 3 o'clock. Sorry, excuse me. And then during this time, our battery is charging because we can see that it goes to a negative current. And then when our battery is a positive current, that means that it is being used over here. And as we can see also, when our grid, when our solar is high, our grid decreases, so we use much less of the grid, and this helps with our cost savings. And then finally, the light purple line is our load. So this is what we want to maintain power for at all times. So if we look at this, we can see that maybe we want to slightly increase our battery sizing. So when the solar is not on, that, then we can use our a grid a bit less, and maybe this will help maximize savings. So remember the iterative loop that I was talking about. Maybe that's an iteration we can consider, and then we want to increase our battery, so then we'll go back to the optimization and then come back to the simulation until we are happy. Okay, and then this is just the results that we obtained from our simulation. And now just I did mention that there are a lot of apps that we have. So just to show you some a few of the apps that we have. So this can be used for fault analysis, for coverage analysis, for certification, for load flow analysis. So here's a few apps. So as you can see, here's the fault analyzer, the load flow analyzer, the certification kits. So these are all what we can use to test and verify our system. I'm not going to go into detail about these today, but you can let us know which ones of these would you like to learn more about. Okay. Okay, so as I said before, this is a low fidelity model. So if we just go a bit into the battery, as we can see, it's just an AC current source with some inputs, so that gives us our measurements. And say we want to model a higher fidelity version of this, and say we want to increase. So we would do this because say we want to increase the accuracy of the system, or we want to have better battery control in the system, so then we can move to a higher fidelity model. So instead of using what is in that block over there, we can use something like this, which is a higher fidelity model of the battery. And I'm not going to go into it into too much detail, but what is nice about this is that we have a multi-domains that we can integrate. So as you can see over here, we have these orange blocks, which is the thermal modeling of the battery, and then we have the light blue, which is the electrical, and then they are modeled with each other. So we have the thermal characteristics of the battery as well as the electrical, and they are put together to give us a more accurate model. And then we also have a charging algorithm, which is better control for the battery. So this is just an option which we could add to our main model if you want a higher fidelity within our model, and we can do it to all of the separate components. Okay, so now we finished with our optimization and simulation, and I'm just going to do a quick recap of what we learned. Okay, so a recap of the optimization workflow. So first, what we had was we had our input power data. So this was, we had ours in a CSV file, which I converted to MATLAB data, but you can have it in a database, you can have it in files as I had it, or you can have it directly from sensors. Then the next thing is we had our techno-economic optimization, was our algorithm. And remember, we had our 4 steps for that, which was we defined our variables, we then defined our constraints, we defined the equations we wanted to optimize, and then we solved our optimization problem. Then the last thing we did was we tested and validated our model with simulation. Okay, and just to recap on the testing and validation, so I did not show it in the model, but there are also a whole lot of apps that we can use. So we have the fault analyzers, so we can inject faults into our systems. We can see over voltages, over currents, all those type of things. Then we have our load flow analyzer, so we can see how the different loads and powers. And then we have our certification kit, so this can help us with certification. And all of these are apps, so it's an interactive environment and it's easier to use than code, and it is quite well documented, so you can just search for these online and it will come up. Okay, so now that we went through our optimization as well as our simulation, we are going to go through our machine learning as well as our AI. So before we do that, I would just like to speak about some considerations that you have to take into account before deciding when to, when deciding when to use AI as well as machine learning. Okay, so the considerations include so I'm going to be comparing using AI and machine learning versus simulation engineering. So first we have to consider our data. So when using machine learning or AI, we need a lot of data as well as quality data. So for AI and machine learning, they have this saying that if you put garbage into the model, you get garbage out of the model. So you really need a lot of good quality data for if you want to perform machine learning or AI. Whereas with simulation engineering, you don't need a lot of data, but you need a deep understanding of the physics laws of the system to simulate it. Also, to do with complexity, if we have very complex nonlinear problems, this is when we use our machine learning, because if we use simulation engineering for very complex nonlinear problems, even though we may have the physics laws or the understanding to build these models, it might take us a really long time and might be very overly complex. So this is another consideration to take into account. And the final one would be system knowledge. So if you are modeling any system, whether it be with simulation or whether it be with machine learning or AI, you need to have some sort of system knowledge. But with machine learning, you don't need to have a deep understanding of the physics laws and the principles. You can have a slightly less understanding of these laws, but you need to understand how the data is related to each other to create the model. But with simulation engineering, you obviously, as I said before, need to have a very deep understanding of the physics laws. Sometimes I would suggest that it's not like AI versus simulation engineering. I think they both have different strengths that can be used with each other. So with AI and machine learning, for example, it is really good if you have, a lot of data about faults. So it is really good at detecting anomalies and finding patterns within the data. Whereas with simulation engineering, you can use it to predict faults that haven't happened yet. So they both have their strengths and they can be used with each other to get a better overall solution. So as I said before, for our predictive maintenance, so this is our super solar case now. So our super solar company was happy with our sizing of our microgrids, so they implemented the battery as well as the PV system, and now what they want to do is they want to perform predictive maintenance on the batteries with deep learning. And why would they want to do this? So the first thing is the batteries have very complex and nonlinear aging behavior, and this is because of their various uses and conditions. Even if it's from the same manufacturer, they have a very different aging behavior, and this causes their remaining useful life very hard to predict. So what we want to do with our deep learning model is we want to forecast when the battery will fail, and this will help us with cost savings because we can plan our maintenance well, and then we can also know when we need to get new batteries, because we'll know when the batteries will fail. And then also it's adaptable to new conditions, our model. So these are the reasons that we want to use deep learning in the first place. So I'm going to switch back to our environment to show you the script. Okay, so this is our battery cycle life prediction using deep learning. So as I said before, the reason we want to use this is that the charging cycles for the batteries are quite different. So as you can see, here is the data set of the cycle life. So it ranges from below 400 to above 2000, which is quite a large range. And this is batteries from the same manufacturer. And so this is why we want to use deep learning. And just to go through the machine learning workflow very briefly, first we have our input data, which is our files, our databases, as well as our sensors, just as I mentioned for optimization. What we do once we have our data is that we're going to pre-process this data. So in our case, we are going to do data transformation because we need to get the data into the correct format for the deep learning to work. So in our case, we are going to use a neural network, and then this reads data in a specific format. So that's why we do our data transformation. After we do this, we develop our models, and then we tune the hyperparameters to ensure accuracy for our models. And then the last step that we can do is we can integrate it, so we can either make it an app or deploy it to an embedded device. I know that everybody might not be familiar with machine learning and AI, and maybe it's a bit much, but just to mention that we do help. If you are interested in these things, we do help coming up with solutions with machine learning and AI, and it is one of our competencies, so we are quite good at it. So if you are interested in AI and machine learning and you don't have a lot of experience, then we can help you. So just let us know if you're interested in it. Okay, just to get back to the workflow. So first we have our data, and we just want to just have some insights on our data. So we just extract our data. So sorry, I forgot to mention we have data for 40 batteries. And what we have in this data is we have our current, our voltage, our temperature, as well as our capacity. So we just extracted data for one cycle for one battery. And as we can see, we have our voltage over here, we have our current, a temperature, and a discharge capacity. So if we look at our data, each of our data has different charging policies, but it has the same discharging policies. So the first thing we want to do is only consider the discharging of the battery. So that is our first transformation on the data, which is part of our pre-processing in the workflow. So as you can see from this graph over here, we move to this graph, and our discharge, if we analyze our data, we see that our discharging is 4 when the voltage is 3.6 volts, which is when the battery is charged fully, and then when it's just discharged fully, the battery is at 2 volts. So this is what we use to ensure that all our batteries was only considered the discharging data. So we had our data, we just extracted the discharge measurements. And after we do this, what we want to do, as I said before, we want to get our data in the correct format so that our neural network can read it. So neural networks read image data. So this is RGB channels. So what we do is we transform our data into a 30 by 30 by 3 matrix so that our network can read it. So now we finished get our data, we transformed our data, and now the next step would be to build our neural network. So what we do is we have these few layers in our neural network. The first is the image input layer. So this treats our voltage, discharge capacity, and temperature as the different color channels, which is our RGB channels. We then have convolutional layers, and then this applies filters to our images. We have the normalization layers, and this speeds up the training of our network. We have our ReLU layers, which performs threshold operations to each element. We then have our pooling layers, which reduce the size of our feature map. So with our feature map, we only want to extract the most important features. So this is the reason for this layers. And then we have our fully connected layer, which combines all the features into a single output. Then the next thing we do is we adjust our hyperparameters. So this includes our learning rate or our batch size. And then this just helps increase the accuracy of our model. Then the final thing we do is we evaluate the performance of our data. So as you can see, this is the performance of our data for 5 batteries. You can see that the predictions were quite close to the actual value. There was, however, an error of 35%. I know this graph can be a bit difficult to read, so I just did one for example. So what I did was I took the first cycle of a battery and then I used our model to predict the cycle life for this, and it came up with 999 cycles. And then I compared it to the actual cycle, which was 1062. So as you can see, our model is fairly close to the actual values, but the way that we would improve this is that we would need more data. We do have more data. Just for the purposes of the demo, we didn't use all, because the more data you have, the longer the model takes to train. So just to reiterate why we did this. So we did this to predict the remaining useful life of our batteries, and this is helpful for our cost savings for our customers, because then we can plan maintenance properly and then plan how long the batteries are going to have downtime for, and as well as purchase new batteries if necessary. Okay. So that was the whole workflow where we went through the optimization, the simulation, as well as the predictive maintenance. So just to reiterate which tools were used over here. So for the optimization, we had our optimization toolbox. Then for our simulation, we had our SimScape electrical, SimScape battery, and specialized power systems. And then for the final part, which was for the machine learning, we had statistics and machine learning as well as deep learning. And all of these are toolboxes on the base environment of MATLAB as well as Simulink. Just some closing comments I have is that we use the use of simulation tools enables us to have optimized solutions. We can perform different scenario analysis, so we can test for all different scenarios as well as conditions, and it is a really good for testing and validation, especially if you want to save costs. It can also really help with streamlining design. And then also, AI and machine learning are very powerful tools, and I know lots of people are really excited about using them, and they can be integrated with simulation to solve complex problems. They don't need to replace the simulation, because AI has certain strengths as well as machine learning. But just remember, always take into the considerations before choosing which tool to use. And then lastly, just about us, is that the MathWorks tools is a single platform solution. So as you can see, in one in one workflow, we did the optimization, the simulation, as well as the machine learning and AI. And one of the strengths that the MathWorks tools has is that it has a multi-domain environment, so we can incorporate all different types of components: electrical, mechanical, thermal, fluids, and it is all in one environment. And just to mention, I hope that you learned something here today and it was interesting. And if you want to learn more, so we do offer training. So this can come in the form of self-paced training as well as in-person training. And then we also have, if you need any help with projects, we also have consulting services where we use our competencies to help you solve your problems. And that is our training and consulting services that you can be aware of. One more thing before we close off, there is also, we have recently have a partnership with Opal RT, and what they do is mainly hardware in the loop testing. So this is used to validate like very complex microgrid systems, especially for control and then the protection of systems. So what you do is you plug your simulation into this, and then you also test on your controller if your simulation is working correctly. So this is just a nice add-on. So if you are interested in this, please do let us know. We'll also be hosting a webinar with Opal RT next quarter, and then whoever is interested in this, we are going to send the link to the webinar in the mailer, and then the mailer will also include our recording as well as our presentation. Finally, I would just like to say thank you for listening and attending. I've attached my email address below if you have any questions. And I also know some of the examples we did were quite simple, but I have attached this more complex example for microgrid where it has a much higher fidelity. And then I attached all the examples for specialized power systems as well as for Simscape electrical. And thank you for listening. And just one more thing to mention, we will also be launching a podcast that talks about this webinar within the next month. So thank you very much, and please let me know if there's any questions. So if anybody has any questions, you can unmute and ask me now. Yes, sure, Vincent, you can go for it.
All right, thanks. I just wanted to ask in terms of the cost savings. I didn't get much of the information from the presentation on to how do you actually assess that cost savings that you talked about. Thanks.
Yeah, so in this presentation, I didn't go into detail about how we're going to assess the cost savings, but if you are interested in that, we can. I think there was a poll that went through about how to go through a cost savings workflow. So we can, if you are interested, we can show you some more demos or have some conversations about how you would like to do that. So it's not included within this demo, but we can have more discussions on that. What is included in this demo is that we just sized our components, which was our PV as well as our battery, to ensure that we use as little grid as possible, while also at some points feeding back to the grid, so we ensure maximum cost savings. So that was what happened in the demo.
All right,
Does
yeah, thanks.
Are there any other questions?
Uh, okay, I see you included more examples for islanding. Just wanted to ask about if you have probably other examples instead of the grid connected ones. But I see the slide that is reflecting there. Thanks.
Yeah. If you have, do you have any specific examples you are looking for?
No, I just wanted a microgrid which is um, off grid, that is not connected to the grid, and to see how you're gonna be looking at the cost savings in that terms. Because I heard that you are saying here the cost savings you are looking at when you are not using the grid, but now in terms of the off-grid microgrid, how are you gonna be looking at the cost savings?
Oh, so you want an example of just an off-grid microgrid and the cost savings.
Yes.
Okay. I will see if I can find one related to that and send it to you.
All right, thanks.
I'm just gonna leave it for a few more minutes to see if there's any questions, and then if there's no questions, then we can end the session. Also, just to mention that this was just an introduction to see all the different tools that can be used for our microgrids. So if you have anything that you want more specific detail in, please do let us know. So you can let us know what interested you and what you would like some more content on, and we can help with that. Okay, okay, cool. Thank you. I think there's no more questions, so we can end the session now. Thank you, everybody, for joining, and I hope you learned something. Thank you. Bye.